some approaches to indexing space by Christopher Foley.
Sounds really impressive.
That's pretty
This is
impressive.
gonna be a real letdown.
Okay.
Do I begin now?
Yeah.
Alright.
Let's see how you use these.
I'm getting there. Alright. So I decided to do this one kind of on the board, not just because I was busy, but also it is a little bit more interactive. And it also, doing things on the board is a little more conducive to the hand waving I'm going to be doing. It's a lot easier to be less rigorous and direct you to the papers when I'm like, well, you know, I only have so much precision with a marker, go find someone who knows the real answer. But despite that, you can try asking questions and I'll try answering them if I know them.
What is space?
That comes up later. No. In this case, we're going to be first talking about one-dimensional space, which is really boring, but really easy to index. From there, we'll get to two-dimensional space, which is like a product of two one-dimensional. That's not important. Anyway, and I'll kind of dabble on N. That's kind of a corollary, because, you know, 2 and N, the whole thing. So part of this talk will be probably boring, well not boring, uninteresting to some, because I'm going to kind of start at a basic-ish level. So I'm going to be covering some data structures that you probably already know, but hopefully I'll get somewhere interesting by the end of it. So first, indexes. So if we've got a bunch of numbers, like 1, 2, 3. I had to think for a sec. So basically, the gist of an index basically is you've got some set or sequence or however your particular data set is interesting. And you want to find something about it. You want to find if an element is in the set, you want to find the nearest element to some point, you want to find a range. So the easiest way to do that is the stupidest one, which is just to go through all of them and look. So you've got some list, let's say, of numbers. You want to find out if 3 is among them. The easiest thing to do is to be like, all right, it's not that one, it's not that one, there it is. It's in there. Or I get to the end and I'm like, okay, it wasn't any of them, so it's not in there. Doing a range, again, you can go through, you can be like, all right, greater than 2, no, no, yes, yes, less than 4, you know, okay, now we're over here. It works, but as n, the number of things in the set grows, set or C, it can become a lot more arduous to have to go through every element and look. So the hope is to build an index, which is just a way of getting into the data in a way that's a lot more kind of easy to chew on. One of the kind of, not even an index, but I'll talk about it anyway, is, the other thing is, in this talk, it's going to sort of, because we're talking about indices, which is a little bit of a border between theoretical computer science and practical computer programming. Occasionally the line's going to kind of blur where the Turing machine falls away and there are practical concerns. Because otherwise you can pick the dirt simplest index and it's the perfect one. For one dimension. But in the kind of practicality of the real machine, certain indices are even worse but perform substantially better. Theoretically worse, but practically perform substantially better. So the first thing is just sort of like the whole binary search. You've probably heard about it if you're at this talk, but if you haven't, don't worry, I'm going to labor over it. So the idea basically is if this, rather than being a list, was an array, or whatever, let's go with array. Something with random access. And you have them in some sort of order, then you can start being a little more clever when it comes to finding things. So you have, 1, 2, 3, 4, 5, you're looking for 4. So you can be like, well, I've got 5 items in here, so the first place I'm going to look is right here in the middle. I know it's in sorted order, and I know that before, or that 4 comes after 3. Let's just assume we know that. So I know that it's not in this part of the tree. I can exclude that right off the bat. This is the magic with the index, is choosing items I never need to really look at. So then I can be like, all right, I know it's in this half, and then because odd numbers are hard, or even numbers are hard, I can be like, well, let's say for interest's sake I picked this one for some reason. To jump to, at this point I know that 4 is less than 5, I can exclude this non-existent part of the list over here, and then I can be like, oh look, there's 4. And if 4 wasn't there, I can decide, well, I know that 3 is here and 5 is here. This is where 4 should go. There's nothing there, therefore there isn't 4. That's sort of like thing. But the problem with this is that, again, in the practical world, or even not even that practical, you have a lot more concerns if you don't want to store things in this contiguous group of space. Because in, say, a list, you get to the point where you don't have 1 through 5 in a block you can just jump in the middle of. You have 1 and the rest. And then you have 2 and the rest, and that's 3 and the rest, and eventually you get to 5 and nothing, and you're like, okay, I'm at the end of my list. So I can't really jump into the middle of it, because they're just, they're points in the middle of nowhere. I don't know where the middle is. I have to find it. So, basically the idea is if we take this kind of approach with the jumps and the middles, we can turn it into a tree. Most useful indices are trees, so this is going to come up a lot. So basically, if instead of my list, I instead put 3 over here, and I can put, let's say, 2 over here, and 1 over here, and 4 over here, and 5 over here. I get a lot more of, I still have like elements that link to each other, but they're sort of arranged in a way where suddenly I can make a lot more leaps. So I can come to the front and be like, all right, 3. Now this is a binary tree, binary search tree specifically, which means there are 2 legs and it's ordered in a very particular way where everything on this leg is less than this node and everything on this leg is greater. Equality we don't talk about.
Things are not equal to things.
It's a set, damn it. No. But basically I can start off my root node here, 3. I'm looking for 4. And I can jump into here, be like, okay, 4 is greater than 3, so I go here, that's 5. 4 is less than 5, I go here, look, I found it. Neat. The other sort of advantage to trees in general is that if I were adding elements to my list, or to my structure, I don't necessarily need to know them all ahead of time. Now, I don't have to know that with an array, but even in theory, things get a lot worse in arrays. If I had 1, 2, 3, 5, 6, 7, and I suddenly wanted to put 4 in there, I'd have to be like, okay, so I'll go 1, and then 2, and then 3, and then 4 should go here. So I'll kind of like put that down here, and then I'll move 5, and then I'll move 6, and then I'll move 7. And that sucks. Whereas in the tree, you'll notice I'm picking very specific examples that people who know what's coming. If I suddenly wanted to insert 4, I can just be like, well, it's greater than 3, it's less than 6, it's less than 5, so it goes right there. And I didn't have to move everything in the list. I just had to like go down the list and find it. So that's the basic gist with the kind of simplest index. This is an index. Okay, so drawbacks. the first drawback with this, and there are solutions to this, but whatever, is balance. This tree looks lovely, and again, it saves me time because every time I want to jump from here to here, I can discard this whole half of the data, and then I can go to here, and I can discard this whole half of the data, and I can get down to here. And I've, saved logarithmic time because the height of the tree and whatever, it's math. That's the kind of rigor I'm going for. But it's not magic that the tree looked like this yet. Yeah, I just built it like this because I knew it would make my point. But it turns out that if I were to go through the typical sort of addition that I've shown you to put 4 in here, and I went through the list like this, I would put 1 over here and I'd be like, great. And then I'd be like, all right, 2. So 2 is greater than 1. Okay. And then 3. 3 is greater than 2. And I end up kind of going like this. And that is just a sideways linked list again, with a bunch of wasted space on this side. It's not a tree. I mean, it is, but it's not the kind that we write papers about. If I was looking for data in here, it would not help.
This is a unary tree.
So technically, when I inserted 4, it would end up over here, but like that's not really giving me a lot of savings at this point. This is not the kind of nice logarithm we want. It's linear. I mean, I chose an example again that's very obvious. It's linear. So that's not awesome. So there are solutions to that, like AVL trees or black trees or all sorts of crap. I'm not going to talk about those yet, but basically we don't have to, but it's very useful for a tree to maintain balance, because a tree that's unbalanced is just a crappy list. So, that being said, most of the data structures I'm going to talk about don't do that, but that's fine. All the good ones do. Okay, so there are trees. Any questions so far? Covering like the first couple lectures of 101. All right. So there are systems where I can go through and I'll start off here, and then when I insert something down here, I'll do like a rotation, or there's some other sort of data I'll maintain to kind of make it so that as I add things in any order to this tree, it sort of ends up being roughly in line with itself, and altogether has nice properties. Those are lovely. We're not going to talk about them. We are, though, a little bit, before we move into the spatial part, we're going to talk about Btrees, because they come up again kind of later. So a Btree, I'm going to pick a really easy one. Basically looks, this would be like 4, doesn't matter necessarily, 1, 2, this is 4, 5, 7's over here by itself, and you go like that. Sure, whatever. Look, it's a Btree. Am I right? Am I wrong, anyone? Okay. Someone tell me if I'm way off base. So, this one, interesting property. The first thing you might notice is that it has more than one data point at every node. Node is this part of the tree. These are children. Anyway, so it has more than one data point. Some of them are full. Some of them are empty. Well, not empty, but none of them are empty, but some of them are not full. We'll call them half full or half empty. You can decide which. Lovely. So the gist of the Btree, and as you add stuff, it has sort of a structure that keeps it so that it always has the same number of levels at number of nodes at every level. This is great. If you have a Btree like this, other self-balancing trees end up being equivalently structured, have congruent operations to this kind of Btree. And as you add things, you essentially do the same sort of thing as before, where, except this time you have two options, and this is the thing that's less than this item, this is the thing between these two items, this is the thing that's greater than these two items. It seems like a relatively minor addition, and it kind of is, but in practice it matters a whole bunch. And I'll talk about why in just a second. But basically, when I want to add 8, I can come to here, I can say, okay, it's greater than 6. It's down here, I'm at this leaf that has no children, so it should go here, and I find the slot, and I add 8. Great. If I want to add 9, I have to make sure I get this right, or I'm going to look stupid. Well, moderately stupid. 9 is greater than 6, it goes into here, so I kind of add a 9 over here, but it doesn't fit, so then I have to split. I'm going to do this live, and I'm going to regret it. So that sort of takes my 7 and 9, because that's the thing, and it moves kind of 8 up to here, sort of. This is the bad version of the algorithm, by the way. So then I have 3, 6, and 8, and then I can kind of draw another thing where 6 comes up to the toppy top by itself, and then we have like 3 over here by itself, and 1 and 2. I did 6 in that up there. No, I totally did. And then down here we have 8 by itself, and then 7 ends up over here, 9 ends up over here, or something like that. It's not going to work. I think I messed up something in the middle here. But anyway, and so in that sense, we've kind of moved up. All our trees are the same amount. Still, we have some more space now, and we still have this sort of nice tree structure that we like. That's lovely. And if you want to know how to really do it, go read Wikipedia, because I kind of hand-waved my way through it. So that's great. There are different kinds of Btrees. Some of them are fancier. I'll talk about that in a sec too. So the reason why the Btree, though, is popular compared to a lot of these other trees is just that for a practical computer, it's a lot easier, it's a lot faster. And the reason is that in a practical computer, when you go to load one of these nodes, jumping really quick out of theory for practical reasons, if you were to build a complete linked list tree structure, you've got like your node here, and this has a little box in memory somewhere, and then it stores the data, and the pointer to the left data, and the pointer to the right data, and then while you're searching, you look at this, you say it's greater than 3, so you jump to the point in the memory where this thing points, and that gets you down here, and you do that, then you jump down to this point, that gets you down to here. That's great, but it turns out that computers, due to optimizations decided on in the early days, for very good reason, are a lot better at large contiguous areas like this array I had over here earlier. So loading this in and looking at it, and then immediately making a jump and loading this in, and then looking at it and making a jump and loading this in and looking at it and immediately making a jump, I said that with a lot more words than I had to, so it sounded like a big deal, is long compared to loading 100 things in and just walking linearly through the list. So the reason why the Btree gets traction and its descendants, which are more useful, is because of this property here. And so what you can do is you can essentially dial up this number so that there's 100 items at every level, and you end up with a tree that if you put 400 things in it has like 2 or 3, I guess not 2, but 3 levels of tree, and it seems really inefficient because you've reduced all this logarithmicness into like 2 levels, which doesn't seem to get you a lot of benefit. But you do get a lot of benefit because you can step here and walk through 100 items in less time than it took to load 1 extra node. Realize that none of these are right, pick the one you want to jump to that, and load another 100 all at once. So that.
And they're sorted inside that. So
oh yeah, and they're sorted, yeah. So you can still do, yeah, you're
so
right.
you can still binary inside the directories.
Yes. So this comes up a little bit later when I'm talking about sort of the more practical indices, because in the end, most of the ones that people use in like heavy applications have some element of this back in it, because it turns out to be kind of a useful property. Whereas, and this is kind of what I was talking about earlier, in theory, like in big O notation, this tree over here properly balanced and this tree over here properly balanced are like identical in properties. In practice, this one ends up being way faster if you're actually chewing through large amounts of data. So a lot of the file systems and stuff and things that are expected to keep track of a lot of information we use, I mean not all of them, but we use some, one of the B family of trees. Yeah, so I mean, like I said, there are B plus trees and B star trees and B all sorts of trees. Yeah?
What does the B stand for?
It's according to Wikipedia, it's a bit of contention because no one's 100% sure. But one of the guys, the primary guy, or the guy who invented it was working for Boeing at the time. So there's a theory that it might be Boeing, but I don't know if there's necessarily an answer. It's certainly not binary, which confuses a lot of people because they start off with like, so this is a binary tree and this is a B tree. It's like, oh really? So like binary? It's like, no, B trees are not short for binary trees. It's a completely different thing. Yeah, that's my understanding. I don't know if there's a more reliable source than Wikipedia, but that's what I got for you. Okay. I think there are a couple other theories, but I don't remember those ones because the Boeing one is more fun. So, that's great when I have one dimension. I have 3, it's definitely less than 5, and way less than 6. Really easy, because I can do this. So the problem with 2 dimensions is that you start ending up with, you're like, all right, I have this point over here, and I have this point over here on my little graph. And I want to figure out what is less. Is this one less, because like this one's more kind of in this way? Or is that one less, because it's more over there? Are they the same, because they're like roughly equidistant in, not my handwriting? And that's kind of, that noise is the whole problem with spatial indices. So, the easiest way to solve it, and that's really not practical, is to just pick a dimension that you've decided is arbitrarily more important. This can work. So you could be like, okay, I like X. So I'm going to say that, like, let's say this is, 3, 1, and this is 3, 1, 3. 3. Should have gone with 2 plus 1. So I can just kind of arbitrarily decide that this one comes first, because that's a bigger number. This number's useful for tie breaking, but like, I can just kind of linearize the whole 2 dimensions. I could pick some like, I don't know, like Hilbert path or something. It doesn't really matter. I can just take my 2 dimensions and boil it down into 1 and just pretend. In which case the tree will look exactly like this and we're done. We just have more numbers in our 1-dimensional comparison. That's okay. And if all you really wanted was set operations, maybe
Membership.
like set membership or that kind of thing, that works fine because you don't actually care about space really. You just have this complicated 1-dimensional point. And you can use the same sort of efficiency to just be like, all right, well, it's not here because 3, 1 is less, and so I look over here and I see 2, and over here I see 1, and I find 1, 3 down there somewhere, and I still have to ignore all of the things this side of 3. That works. But there are a couple operations that people tend to like doing on space that it's really kind of bad at. So the first one is the whole kind of nearest neighbor approach. So basically I want to find the closest restaurant to this location. Linear index is kind of typically pretty crap at that. And the reason is that kind of like this right here is physically close to this dimension, but this is in this case, infinitely far away, because I've got like this and this and this and this until I kind of get here. But it's actually really close. But in terms of my linear index, it's somewhere in the middle. It's kind of completely separate from the point I'm looking for. So I can't actually easily decide where to look. I have to look everywhere just to find, and then like, again, I have to go linearly through this tree and be like, well, that's pretty close. Oh, that's closer. That's not very close. That's kind of close. That one's closest so far. No, no, no. And then like, I pick the closest one. That's not awesome. That kind of defeated the whole purpose. And, well, yeah, let's just talk about that one. There are other ones like the whole k-nearest neighbors, which goes even further. There are range searches where it's like I want to find all points within this box. That also sucks because I have to like find here. You know, if I get to 6, which, you know, is like here or something, I can't just stop looking because it might be to the left of 6 and down. So it's okay for set operations, but it's not actually good at the whole like space thing. It's just, you know, if you have multi-dimensional points, but you don't actually care about space, then it's fine. The next kind of approach, let's just leave all that. The next kind of approach is like, well, I want to actually use these dimensions, not just one of them. So what if, but I still want it to kind of be like this tree. So what if up here at the top, I'll do this whole 3 greater than 1 thing. So that'll be okay. So I can kind of divide here. I'll be like, this is all on the left and this is all on the right. Sure. But I want to be able to use these other dimensions. So when I get down to my next level, what if I decide then that maybe I'm going to go Y from now on? And so, you know, my subpoints can kind of be here, that's on the left, and it'll look like that. And then this point over here will be like up here somewhere, it'll look kind of like that. So now, if something is greater than 3 and less than 2, if something is greater than 3 and less than 2, then I know it's here. I can ignore everything greater than 2 in this half of the y, and I can ignore everything less than 3 in that half of the x. That can work. That's called the KD tree. And then, you know, the next level down, I go back to x because there are only 2 dimensions. So now there's a point over here, so I draw a box kind of like this. That can work. So now if it's greater than 2 and, you know, less than whatever, didn't leave myself a lot of room in my numbering scheme there, 3.5. Then I know that it's over here, and I know the only reason I'm in this quadrant at all is because it's greater than 3. That's something I just know. Which means if it's not over here, then it's not anywhere in my space. So this one's okay. And so if I wanted to do a range search like this one, or we'll do a range search. Basically what I can do is I can start off at the top level, which is this line that should be slightly, why did I use orange? So I can look at my box here, and I can look at this line, and I can be like, okay, my box intersects this left half, so I have to look over there. And my box intersects my right half, so I have to look over here too. Not the best thing in the world, but it's, you know, whatever. So then I go over here, and my new box is kind of under here and above here. My box does not intersect up here, so I can now discard everything that's on this whole part of the world. I only have to look over here, and I can look and see that there's that guy. I'm not sure if he's part of this data set, but let's say he is. He's not inside the box, so he's not included, done. Now I can go over to this side, and I can be like, all right, it intersects below me and above me, so I have to look at everything again. So I look down here, I see that, you know, this thing, this box, this point is in my rectangle, so I include it. I look up, I have this side and this side. I can exclude everything over here because it doesn't come anywhere near my box. Now I only have to look on this side and I'm done. I don't have to look at anything else because I know that they have nothing to do with my box. That can be argued. The same thing sort of with the nearest searches. I'm not going to go into this much detail on the algorithms kind of for the later ones because I'm kind of covering it all right now in the intro to what things you do in space. But again, if I wanted to do sort of if I wanted to find the nearest point to this one, I can start off at the top and be like, all right, it's this far, that's kind of the mark to beat. I can look over here and I can see that my X is closer to this side of the world than it is to my point. So maybe there's a point like right here that is closer than this 3, 1. So I have to look over there. X is straight up in this side, so I definitely have to look over here. So I can go over here, I can see that there's no point closer than 3, and this side is way further than my current best choice. So I don't even have to look, because any single point over there is definitely further than this one from X. Then I come back over this side, I see that this point is pretty close, but because X straddles my line here, I have to look on the top and bottom, because maybe there are points closer to infinite. I come over here, this point is way over here, I don't care anymore. There are no other points down here, so we're done. So this is my closest one, and I was still able to kind of skip things. Yeah?
Wouldn't the point you'd be checking is actually the intersection of the old line with the new point? The perpendicular from the new point? Because that's the closest you can be, right? Instead of checking the point itself, shouldn't you be checking the perpendicular from that point down to the old line you are currently at?
This one?
Yeah.
No, sorry, I'm looking for something closest to this X.
Yeah.
So the only distance I care about is this one.
So you actually want to set distance from the set that's still being considered to the point you're looking for.
Yes. Oh, I see what you mean. You mean check it from here. Yeah, you're right. Because there might be a point right here that I don't know about that's closer. Yes, you're right. In this case, I used my human oracle knowledge to know that there wasn't, but yeah, you're right. But in this case, this line is further than that point, so I know still, but yes. So that one's okay. The KD3 is okay. It's fine. The kind of main problems with it is that in more than 2 dimensions, it gets really sort of useless. Because it's doing this alternating at every level thing, you have to go 10 levels down before your 10-dimensional point even gets back to X again. And so you just end up with all these perpendicular slices that don't actually let you exclude a lot. It's really useful from the KD tree's perspective when you can start getting into this sort of structure, because then you can start kind of zeroing in on the boxes you care about. But yeah, in 5-dimensional data point. Yeah.
Isn't it true that even in very high dimensions you exclude roughly half the points? If you choose it.
You can, but especially with ranges, you end up your ranges sort of tend to kind of cut across a lot more boxes because your range, by definition, your range is 2 by 2 or n by n. And when you're only splitting on 1 dimension every time, you're not excluding as much. The same thing is true with the nearest neighbor there, where because your sphere over here and the random vector that crosses them drives right through dimension lines, you can end up with a point that is closer that you couldn't exclude in any dimension because it might have been closer. So yes, if you're looking for set intercept or set membership, and just if you're just looking for a point, you do still exclude half of your places every time. But again, you could have used the linear method if that was all you were interested in. The other problem, and again, there are probably solutions to this, but in the kind of really simplistic definition of KD trees, they end up with the same sort of balancing issue that the simplistic definitions of binary search trees does, in that if you're adding points that look like this, you end up with like, all right, so I'm going to split here, and 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 you like, it doesn't actually do a lot. You're just linear again. I'm sure there are balancing KD trees. I've just never looked for them. Probably. There are probably balancing KD trees. Yeah.
What does KD stand for?
K-dimensional? I'm guessing that right off the top of my head. But it sounds good though, right? Oh, is it authors? Oh, that sounds even better. Let's go with that one. It could have been crafted. I don't know. Maybe that was the author's favorite things. There was one other point I wanted to make on the KD. Oh yeah. So the KD tree, there's probably balancing versions of it, but again, it gets a little trickier than the one-dimensional case because you've orchestrated your splits like this. You're starting to end up with the case where you're like, okay, if I want to rebalance here, oh, that's not where my point was. If I want to rebalance here, all I know about these points is that they are less than this. And that's kind of it. So to rebalance, there's a lot more you kind of have to look at. I'm making this up as I go. Because you have kind of less guarantees in the one-dimensional stuff. So like I can't necessarily just move this child point up in the middle and then drop it on both sides, because now it might not be the right structure because this subnode's in a different dimension than the one that I'm currently trying to shift. Might be fine. I'm sure there are algorithms for it. I don't think anyone looks because they just do something else.
Could you just do a dimension at a time?
The balancing?
Yeah. So instead of dropping the child from one level down, take the child 2 levels down.
Right, just be like, okay,
on
he's
it.
now my thing, and then, yeah, probably. Sounds good. I like that. Yeah. The other thing is, well, I'll talk about that at the end because it applies to all the trees. Okay. So, the next one that I'm going to talk about real quick is the Quadtree. A lot of people probably know about this one. I don't really care right now.
Do I have a quad after KD? That seems backwards.
Nah, it's got a flow to it, don't worry. I mean, I think it's got a flow to it in my brain. We'll see. So there are two kind of approaches, well, I mean, there are kinds of approaches to quadtrees. But I'm going to talk about two. So one of them is spatial, and the other one is points. But basically the idea is, so I've got this box in which things are. So what I can do is I can be like, all right, I want to subdivide it kind of like that in 4, and this one gets subdivided into 4, and then this one gets subdivided into 4. And so I've got this division of space. And what it gives me here is, oh, and then like there's a point here and a point here and a point here, something over here. And it kind of builds into this structure where it's like this is 1, and then 1 has 4 children exactly, which are 2 and 3 and 4 and 5. And then 3 over here has 4 children, which is 7 or whatever, not important, and that has 2 points or whatever. Anyway, so this has, the main property with this one that's interesting is that it allows you to actually sort of define space a little bit more. Because if there's a box that intersects here, I know it's in my first child and my second child, and it's in the first and second child of that subchild and the second and fourth subchild of this one, and the rest is not. Because I've got this, like, I've covered kind of all 4 options that two-dimensional space gives, rather than breaking it down into different kinds of one dimensions. Up until now, either it was all one dimension, I just kind of made it up, or with the KD tree, I kind of alternated dimensions, but it was still really a one-dimensional thing. With the Quadtree, I have greater than x and greater than y, and also less than x. I didn't say anything. And I also have greater than y and less than y. And so a point goes in this place. It always is this side over here, and I can really exclude the other 3/4 of my range. That can be okay. The main, so that one's space where I kind of build this structure ahead of time, and it just kind of sits there empty. No one really does this, but I'm talking about it anyway. It just kind of sits there empty, and then I can, when I want to put this point in, I can be like, well, it's greater than x and greater than y, so it's here, and then it's greater than x and greater than y, so it's here, and then it's greater than x and greater than y, so it's here. Done. The other kind of advantage of this one is you can sort of approximate back up the tree if you wanted to. You could store data at these nodes. So for example, like just off the top of my head, you can store a count. And you can be like, all right, so 3 has this accessory data of 2, and then 1 has this accessory data, or this one has 2, and that one has 1 and 1, and this one up here has like 4, I guess. And so you can sort of, I don't know what that's for, but you can sort of do something with it. Because it subdivides your plane here, and be like, all right, I know that there are 4 points. I don't even need to find them, I just know that there are 4. And if I care what they are, I can go looking for them. So if I was like approximating an image from a distance, I don't know, I'm making stuff up as I go, I can be like, all right, it's kind of like there are 4 pixels out of, n in there, so it's kind of like mostly white, but there's some black in there, sure. And then if I want more resolution, I can go down and down and down. The disadvantage is that it wastes a ton of space. For my whole structure here, with 4 points in it, I've got this like multi-legged, exponential tree going. It's not exponential, but anyway. That's kind of crazy, but if I have a ton of space, this is fun. The other one, kind of similar, but still quad, is the points one. And basically, this one, very similar. But it's based entirely on points, so I've got my space again. I put a point down, and it goes here, and then I'm like, all right. Now this one's sort of like the KD tree again, but in 2 dimensions, so I can be like, all right, that's my first point. I put it on my map here. And then my second point is greater than this and less than this, so I can put that here, and it kind of does this little doohickey. And then this point's over here. And so you can kind of end up building this structure out of points. It still wastes some space because, for every data point, well, that's sort of, again, another practical issue with indices, is that they are useful, but they are a trade-off, because just storing the data on its own in a list is always more efficient than putting it in a structure with all this like lookup data. In theoretic land, we have infinite tapes and we don't care, but sometimes in a real computer, if you were having like a database of restaurant locations or something, it would be unfortunate if for every one restaurant you had like 9 accessory pointers that didn't really help. Or like helped, but maybe not enough or whatever. So that's sort of the trade-off. So this is, again, it's okay, there's some wasted space, and you still can end up wickedly unbalanced as, you put this point in and it looks like that, and you put this point in and it looks like that, and you put this point in and it ends up like that. Again, there are probably algorithms for balancing these, whatever. This one, I feel like, just off the top of my head, would be easier than a KD tree, just because it's always kind of stable, but I don't actually know. I'm sure in the end it's all logarithmic. So the main disadvantage of this one is just that it's got kind of a high space expenditure. And the other disadvantage with it is that it's called a quadtree because 4, 2 times 2 is 4. But the 3-dimensional variant is the octree because you have the same thing greater than z and less than z, and then like the 4-dimensional one is with 16. So as you go up in dimensions, the structure still kind of works the same, but you end up with like 16 pointers for every 1 data point, and that gets kind of insane. And then you have to balance that. Anyway, quadtree, roughly. But if you were doing a range query, you could get all of your stuff again, where I know that this intersects this, so I can go here, and then I can this, and then I can still exclude a bunch of stuff. Okay. Yeah. So the next one is the one that almost everyone actually uses a variant of, and that's the Armory. Boo. I don't like it, but a lot of people do, and it's probably for good reason. So, the Armory, this one's where it gets a little more hand-wavy, just because, we'll talk about this. So the way the Armory works is I've got my space, and I insert a point here. And what I do is which one of these is better? Which one of these can the camera see? You know what, I don't care. Oh yeah, orange is better.
Use the orange one.
Yeah. So what I can do here is I can have this data point. That's great in this finite space. And to ease lookup later, because rectangles are easy, I'll draw a little rectangle again around it. R stands for rectangle. So now in my tree, I can store my property here of my one rectangle. That was a bad choice. One. And so if I'm looking for a range or a point or whatever, what I know is that if the area intersects this rectangle, then my point might or may not be in there. But if it doesn't intersect this bounding box, then it definitely is not. So if I'm doing a range query, you know, 3 colors. If I'm doing a range query over here somewhere, I know I don't have to look. Like I look at the first node of the tree and the answer is nope, definitely nope. Okay, so now I want to insert a different point, and that's when everything gets bad. So if I want to put this point in over here, depending on different implementations, usually what happens is I'm like, okay, well it doesn't fit in my current box, but I need the box to contain everything in the tree because this is my root node. So I'm just gonna go ahead and stretch this rectangle all the way out to here, and now it's got both points in it. So now I'm doing my Now that I'm doing my intersection here, I have to look in the root node at least to see what's in this rectangle because they intersect and that might be important. In this case it's not, but I have to look. So that's okay, and then I insert a point over here somewhere, and then things get weird. So the R tree is kind of like an attempt to take the Btree kind of concepts and make them two-dimensional. So it stores multiple entries at every node. So I have my point 1 and 2 and 3, 2, actually no, 3 minus 1. 2 and 3. Yeah. All right. So that's lovely. And the reason they do this is for the same reasons as the Btree. R trees are used a lot in databases, and the reason is that I can have these chunks of things that I scan through, but load up in this one chunk. Whereas the KD trees and the Quadtrees got kind of spindly. As you put more, that was kind of not the biggest problem, but the most impractical part of them is that as you put more and more entries in them, you end up with these long, kind of gangly trees, and you have to load up this thing just to find out it's less and greater and then jump to the next one. Like I talked about with the other trees, whereas the R trees try to cram them in with these boxes, so they're like, this node contains this area, you should look. So, I get to this point, but I can't fit them, because I'm the worst R tree ever, and I can only hold 2 things. So I have to do something. So basically what happens is I can take my toppy top here and leave it where it is, because it still has to contain all sub-elements. But I have to split this. So I sort of move down my area here into this, and I draw another little box in here that contains these 2, and this box over here that contains that one, and then 1 and 3 go over here, and 2 goes over here by itself, and nothing goes up here. R trees, at least my understanding of them and the kind that I'm talking about, are one of the sort of first pure indices we're talking about, because we didn't talk about the B variants, except the base one, which is not like this, which is that the structure here really serves to find points. It doesn't actually store data, except for the root, because every single tree, except like one, you have to have some special case for the root because you don't have data yet. But anyway, but in general, you only store data at these leaf nodes, kind of, and the other parts are just sort of for organization. So I still have this containment property, so my green box looks in here and it sees, all right, I've got, I intersect this one outer box, so I need to look. Then I look at my two inner boxes, nope, I'm done. Whereas if I add, this data point over here, it can go, all right, I'm going to extend this box up to here now. And then when I look, I can see, okay, it intersects here, nope, yes, so it goes in and finds that 4 is within the box, I'm good. That's okay. The biggest problem with our trees is that I am a magic human oracle, but the computer is not, and I'm really not even that good of an oracle. Because when I extended these boxes, when I did these splits, I picked the obvious choices. Obviously 1 and 3 go together over here. Obviously 2's on its own over here. When I expand it, 2 goes with this one. I'm not going to draw the box, like leave it like this, and then like this box goes all the way across because it has to be a rectangle. And then 2's on its own over here. But like, why not? There was nothing in the definition I gave that said that I shouldn't do that. That's also an option. So the R trees have a ton of heuristics, and basically the benefit to them, but also their kind of detriment, is that a ton of research goes into these heuristics, because a bad heuristic can lead you with a really bad tree. Because the other thing that happens with R trees is that there's no guarantee that they need to not intersect, because they might not. So if I've got a point over here, and a point over here, and a point over here, and a point over here, I could draw a rectangle here and here, and there's like a little bit of intersection, but I can't guarantee that I can always do that. This point might be, here, and then I have to draw the box, and then here, and then I have to draw the box, maybe this one, and then maybe from these or something. But these rectangles can't dodge around stuff, and you can always, pretty sure, end up with intersections between these kind of loose sibling rectangles. And so the only guarantee you have is that your parent contains everything within it. So, there's some box at the root that contains all sub-boxes, and this box has things. But you could end up with a rectangle here, and a rectangle here, and a rectangle over here. And if you look at R trees for large data sets, like American cities or something, they look awful. Because, kitty trees don't look a lot better. But, they're just like boxes all over the place, and they're all touching each other. And that's fine. And if you pick a good heuristic, you can sort of end up in a place where it doesn't overlap a lot and as little as possible, and there are other sorts of variants to R trees that try to sort of do the same thing the variants to B trees do, which gives you a little more certainty and stuff. Yeah?
Why is overlap a problem?
The reason it's a problem is because if I'm trying to find a point or a range, I'm trying to find, this point, I can't exclude as much if all boxes intersect this point. Because I get to here, and I'm like, all right, well, I have to check this child and this child and this child, because all of them could plausibly contain this point. And then I go into each one of those, and they have 2 boxes in that area, because there's a rectangle here and a rectangle here. It's like, okay, now I have to check both of these children, because they might plausibly contain this point, and I have to come up and go to the other child and check that they might, because I can't necessarily exclude children. That's a fun sentence. In the same way that I can with Quadtree or whatever, because with a Quadtree I knew that if my point is like this and the point I'm looking for is here, I know it's not this. I can exclude all 3 of those children, whereas with the the Armory, my children might look like this, and this point I need to visit all of them and potentially all of their children to try and figure out who has this ambiguous point. It doesn't necessarily live in just one location, it could live like kind of anywhere. And so you really want to minimize overlap so that you can not visit as many nodes as you can, because every node you visit is more time and space and stuff. Yeah?
It's around 5 minutes after 8, so
Okay, am I wrapping up soon? Is that the idea?
yeah.
Or, okay, cool. In that case, I'll super speed. So that's the Armory. I don't have to talk about any of the specifics. You can look them up. This would be bad, of course. So basically, the whole thing with Armory is that they're really practical, and like when you're looking at a spatial database, chances are they use an Armory or some variation on that. Because they map to database as well. So like traditional database indices almost always use one of these B variants because they have this blocking structure, and especially the B star tree, or maybe it's the B plus, I don't remember which is which, does the same sort of thing as this R tree, and then it stores all the data at the leaves rather than in the inner nodes. The inner nodes are just there for routing. Maybe both. Anyway. And this is useful for databases again, because your data is down here somewhere. This index is just kind of accessory data, and so you just kind of chunk it on top, point down the blocks you already were storing your stuff sorted in. And then the other advantage is that all your leaf nodes are kind of listed together. So if you're looking for a range, you can do the kind of hybrid approach of looking through your tree to get down to here, and then be like, great. Linear search from there to the end, dun 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 dun, next, dun 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 dun, next, dun dun dun. So a lot of database indices are already like that. And the R tree is also already like that, kinda. But it all comes down to the choice of heuristic. And so there are X trees and SR trees that are kind of popular. But they all essentially are variations on, or heuristics on top of this to try and keep overlap to a minimum and split data so that you end up with kind of a useful structure. I want to talk about two more, so I'm going to talk about it real quick, which is good because then you can't ask me questions. The one that I really like, and was unfortunately kind of second to last here, is called the KD tree, and no one really talks about it, which is why no, not the KD tree, the PK tree. Which very few people talk about, but I found one day because I really hated the R tree, and I was like, there has to be something better. So essentially the way PK tree works is, I like to think of it as a sparse spatial quad tree. So you've got your sort of, division here. Oh, the other thing is rectangles in n dimensions. They work much better than the other things I've talked about, so you can store n-dimensional space in an R tree better than the quad trees or whatever, but I mean they still break down a bit, but everything sort of does because it really does just become more complex. So the way the PK tree works is roughly, you can read the paper, it's pyramid K instantiable. We'll talk about that in a minute. I'm glad I looked that up. It's a sparse quad tree, basically, which means that the biggest problem with the quad tree was just that it had all these dangly bits that didn't really do anything. And it's also got some Btree properties because we like those. So basically the way it works is it's like, all right, kind of like a quad tree. We have these 4 quadrants, or these, n over whatever, 2, I guess. Like we split each n dimension into 2 sides. You can end up with all these quadrants. But it seems like a waste to instantiate a whole quadrant just to hold like a point. That's not very space efficient or memory efficient or CPU efficient. So what they did with the KD tree is they said a node is only created if it's what's called K instantiable, which means there are greater than K elements that would exist within it. So if I have a tree that looks kind of like this, done. All right. Then basically what happens is I've got my root node over here that is the whole box. Cool. And my k is 3, because that's convenient, because it's easy to draw. So, with a quad tree, I would have this, which would have this, which would have a point in it, and would have this would have a point, and this would point. What the KD tree says is it's like, okay, over here I've got this subdivision that has 4 points in it. That's more than 3. So that's going to be a child. I'll call it 1. 1. And then that point has, 1, 2, 3, 4 points inside of it. And this area over here has more than 3 points in it. So I would create that. But if I go one level deeper, I can see that this inner subdivision would have more than 3 points in it. So I would create that one. But if I create that one, then I come up a level, there's only one child now. This child over here. So let's just skip that extra one, and we'll just make this 2. So that goes over here, 2, and it has 1, 2, 3 points in it. And then these 2, no one cares about these 2. They're lonely. We hate them. So I'm just going to go ahead and put these here and here. Tree. So sort of the properties of this one, the weirdest property with it, and the reason why it's not great with databases, is just that there's this mix of points and leaves, or like leaves and subchildren, right? My siblings here, the sibling of this point is a subtree that's 2 levels down and a tree that's like 1 level up. That can get weird, but space efficiently, or like computationally efficiently, it's actually not too bad, because if I'm looking at something that intersects this range, I can be like, no, it's not over here, it's not over here. Oh, that point's in, that point's in. And I didn't have to go anywhere else, because there were only 2 outliers. It was weird to make up a whole node for them. The other property is that it has a minimum fill, which means that, because by definition, every subchild except the root has to have at least k things in it, or else it's not created at all. So I know when I get there, I'm at least going to find k items. I could find more than that, but I'm at least going to find k, which means it's probably worth my time going there. The upper bound, I'm pretty sure, is like 2 or maybe m, where m is the number of dimensions, up to that. So like I could have up to k. So for example, I could have up to 2 in each of these subquadrants before one of them becomes a subchild of its own and then like goes and lives off on its own. So I have this sort of like minimum and maximum size, but it does fluctuate. Which also was something that the R trees sometimes struggle with, but certain R trees are fine, which is that you might end up extending your box for like 1 outlier and then you don't care, but now you've got this huge box just so that that guy can be contained. So that's sort of the gist of that one. It all ends up being kind of logarithmic, but you end up with this sort of nicely balanced structure, roughly. I'm going real fast now. One other neat property of this one, I'm erasing it to talk about one more tree real quick, is the KV or PK trees are unique, which means unlike all the other trees, for a given set of elements, there is one structure that fulfills these k instantiable properties, which means that it doesn't matter what order you insert your points in, you will always get this tree at the end, which is not super useful practically, but it's kind of fun, and it does make the reasoning sometimes a little bit easier in the paper, just because you're able to be like, well, rather than having to be like given a random set of points in a random order, we could expect to find something like this. You just have to get random points because the order is not significant, which is kind of neat. It also means technically, if for some reason you were testing equality of sets, you only have to test equality on each node, and as soon as any node's equality fails, you fail the whole thing. So like if the top of your tree has a 2 and a 5, and the top of this tree has a 2 and a 3, they're not the same. I don't know why, but they're not, because otherwise they would be identical. Anyway, so I like those ones. They have neat properties, but whatever. It doesn't have to be practical. So the last one I really quickly wanted to talk about is a tree that Steve Hanoff introduced me to the last time I talked about PK trees. I don't know if anyone knows Steve Hanoff is cool. I've been watching Steve. So this is the VP tree, and the only reason why this one is cool is because up until now we've been talking about space, which is like, and 1 dimension by 1 dimension or n dimensions or whatever. So that works great if you have pixels or points or moving bodies or whatever it is you're keeping track of restaurants. But sometimes you want to be able to index things where you don't have that property. So I'm going to talk real quick about the VP tree. It's also called the metric tree because it works on metric spaces. So real quick, a metric space, real quick, Cons, is if you have some space where there's always a distance operator between any 2 points. So you can always, there's no nan or something, there's always like a point and a point, there's always a distance between them. Second property is the distance is reciprocal, which means that the point from A to B and the point from B to A are always equal. So like you can't have one-way streets in your Manhattan distance because then it's like, oh, I can go like 2 steps to you, and you have to go like 2 blocks down, 2 blocks back, and come this way for this construction. And it had that triangle inequality has to hold, which means spheres are probably on, right? Anyway. And I think there's another one. Oh, equality is equality. Anyway, so the idea is if you have a space like this, you can look it up. Then the VP tree is kind of cool because it only relies on this distance function. You don't actually have to have points that map to any place in space. It only has distance. So the way it basically works is you've got some point, some object right there. And what they did is that you have some radius, and kind of like a binary tree again, but what happens is that rather than being like greater than or less than, you have closer to and further from some radius. And so you can have a point here, and then that has a circle like this, and then this point over here has a circle like this or whatever. And so your tree ends up kind of looking like this. And so if you're trying to find a point or an object, all you have to do is be like, okay, I have this thing, and it's, the distance is 6 from this point, and my radius is 5, so I know it's not any of these. It's over here. So I can go to this other tree, and then, I can be like, all right, 6 from this, oh, right, the triangle inequality is important again. And so I know that it's not nearer than this, so it's got to be over here somewhere, and then I can find this point and say, oh, that's outside, there's nothing outside, so it's not here. So like examples of this, obviously coming from Steve Hanov, the easiest one is the Levenstein distance, which is the distance operator or a distance operator between 2 strings, which measures the number of insertions, deletions, or additions it takes to turn one string into another string. So if you had, say, a dictionary of words and you were trying to find a word that's close because it's a typo, you can use something like a VP tree to be like, all right, the word rad and the word lad are 1 character apart from each other. So if my radius is 3, then I know it's in. Then I know that my root is rad for some stupid reason, and and lad is within this circle, so I can exclude everything further than 3 characters away from rad, because I'm trying to find lad. Damn, Steve. And then kind of like go this way. Not the different Steve. Vantage point tree. Anyway. So that's kind of cool because it kind of turns this spatial pointy thing into all you need is distance and you can build some sort of a tree. Again, they can end up wildly out of bounds. They don't have the indexing property. I'm sure those people are working on it. But yeah, I just wanted to cover that one because it's sort of like a different way of thinking about the whole problem of space where it's like, yeah, there are like places that hold positions, but like, what if instead I had a sound file and another sound file? They don't really exist in space. They're not even n-dimensional. They're just nothing. They aren't a thing that can be somewhere. It's a sound of a guy going, hey, what's up? Like, it doesn't exist. There's nowhere I can put it. But if I can compute how distant that is from, how far that is from the sound of a cat mewing, I can index it. And I thought that was kind of cool. The last thing I did want to talk about really quick is just all of these trees. Often spatial indices have a bulk loading property, which is a more efficient way to build a tree that is balanced and useful out of a large series of points you know ahead of time, because it kind of skips around the whole balance maintaining. If I already know every city in America, and I'm trying to make a map of every city in America, I can start making a lot better oracle choices if I'm willing to expend the time up front then just insert. I can be like, well, I'm going to pick the one that's dead in the center. That's probably a good first choice. And then I can kind of median my way out from there and kind of build a balanced structure once if I already know all the data ahead of time. So sometimes that's a useful property. Like if I was, again, doing like Cities of America or whatever, it can be a lot more useful to build the data set once. I build this data, this tree, and then from then I just have like efficient queries on it that work pretty well. Whereas other things, like if you were like writing Foursquare or something, like people are popping in and out all over the place. Bulk loading doesn't help. I have to start with like a guy, and then he's gone, and then he's over here. But I mean, some trees only really talk about their bulk loading property because they assume that you have some big data set you want to run like once, and then query against for the rest of time. So that's a real quick and then quicker at the end introduction, and hopefully you got something out of it and at least know what papers to look up if you're interested. Free for questions afterwards, if I'm still awake. I've kind of run into your time a little bit, but...
I'll go fast.
Okay.